Thanks. So I'm Serge.
I'm Adrien.
I'm Juan.
And we're going to present you the work we've been doing over the past 4 years at QuaxLab. So QuaxLab is a small French firm, and we've been working on building a code obfuscator based on LLVM. So we're going to share the process we've made to build that and the lesson we learned and some few other stuff. So the topic. First, I'm going to introduce you about code obfuscation and what it implies. And then Juan is going to present some obfuscation based on LLVM so that you have a glance of what kind of obfuscation we do. Obviously, because most of what we do is closed source, we are not going to go that much into the details of all that we've been doing, but still. Adrien is then going to present a more advanced obfuscation that reveals some limits of LLVM or of our approach. And then, because we wanted users to take control over the compiler, we had to improve the path manager or the way you can schedule paths in LLVM, and we're going to share this with you. And then a few things about testing and benchmarking a code obfuscator. So let's start about obfuscation. So roughly, obfuscation is taking code, it could be source code or assembly code, and transforming it into another code that is more difficult to understand. More difficult to understand for a reverse engineer or for someone who is trying to disassemble your code, any kind of protections that make it difficult to understand the intent of the code. But I'd rather prefer the GNU version of what is obfuscated source code, because it's written in the website that source code that is obfuscated is no longer source code. It's not the right citizen of the source code world, because it no longer carries any valuable information to reproduce stuff. So the goal when you write an obfuscator is to turn white box analysis into black box analysis. White box analysis is you can do anything you want with the code, and you can read the code. So you can take the input, observe the output, and observe how the control flow flows. And from that, you get intel about the code. And when you do black box analysis, you only have the input, you get the output, and from that, you can make deductions. But you can't read the code. And when you obfuscate your code, you've got the code, but it's as if you were in a black box. Looking at the code does not give you any more information than the exchange between input and output. And that's our goal. And we've been trying to do that in LLVM. So we could have done that at the source level, turning C into C, C++ into C++. But then we would be tied to a language or to a specific version of the language, and that would not be as generic. We could also have been doing that at the assembly level, like a Packer would do, but then we would be tied to a specific architecture, and we would not have that much analysis or information about the intent of the code. So at the LLVM-IR level, it's nice. Then we do this obfuscation. So an obfuscation is just a regular path. You've got paths that optimize the code for performance, and an obfuscation is just an optimization that optimizes for security or for obscurity. But it's just an LLVM path, so it fits well into the model. The advantage of relying on LLVM is the one that everybody knows: you're language agnostic, you're backend independent, and that's great. In the context of obfuscation, there are some drawbacks. Obfuscation means sometimes relying on some tricks or on some architecture-dependent stuff. And you can't express most of them at the IR level. You can still do some target-dependent stuff at the IR level because you've got the target layout and stuff, but still that's not the best approach. But as we do ship our product for Linux, for Windows, for Mac, for iOS, for Android, and for ARM and Intel, staying at the LLVM level was the right choice. So we've got this optimization and this obfuscation, and we're going to mix them together. Because you don't want the code only to be difficult to understand. You still want it to run, and to run at a decent speed. So the first thing to understand is that when you obfuscate your code, if you do it in a trivial way, later optimization may be able to reverse them. If you just split a constant and state that's an obfuscation, that's not the case, because any further LLVM optimization will just constant propagate it and it will disappear. So first rule, when you write an obfuscation, they must resist any LLVM obfuscation, LLVM optimization. And then performance is still important. So first run the optimization and then run the obfuscation. And because when you design your obfuscation, you don't want to generate perfect IR, but to have self-content obfuscation, just run optimization once after. And we've got a small graph to illustrate that. The baseline is just -02 on a MD5 run. And the MBA is just an obfuscation. And when you apply MBA after optimization, the code is more obfuscated. It's obviously slower because you add up instructions. But if you add an extra optimization layer afterwards, you get some extra speed up because we don't generate optimized obfuscated code, but just obfuscated code. But the most important fact is that if you run the obfuscation first and then the optimization, then first you are very slow, and then you're not stable at all. Juan is going to explain why, but basically the pipeline optimization, then obfuscation, then optimization proved to be a good one.
Okay, so now this is working.
Yeah. Yep.
Okay, so now I'm going to introduce some obfuscations to see more or less the problems that we have and to see more or less what obfuscations do. So the first case, it's a really nice obfuscation, very beautiful. It's called opaque predicates or obfuscate predicates or opaque constants. It has many names. So this obfuscation will pick a constant in the source code, and it will replace this constant by an expression depending on a random variable from the context, on a variable from the context. This can be fully implemented in the IR level, so that's great. It can be vectorized, and it's independent from the language and from the target. So until now, everything seems awesome. But imagine we have this little piece of code, and we said that we are going to pick one variable from the context. Okay, which one? Do we pick X? Do we pick I? So to not overwhelm the user with this really million of tiny choices, we choose to do it randomly. However, we have to fix a random seed at the beginning of the compilation such that we can reproduce the generated source code. But notice that if we pick X, the looping variable count motion will be able to move the entire expression outside the loop. If we pick I, it won't. So across different seeds, we may get differences in performance. In some cases, huge difference in performance, because we may block or not different optimizations. Another obfuscation is control flow graph flattening. The control flow graph flattening transforms all the branches in a control flow graph to jumps, to a dispatcher block, and this block contains a switch statement that will jump again to the right block. However, there is a problem. We need to be able to change the edges of the control flow graph as we want. And this is not always the case in the LLVM. The typical example are the Windows exceptions. So the invoke edges, we cannot touch them. All the catch switch instructions, all the landing paths, the special landing paths, and the cleanup return and catch return instructions, we cannot touch them. We have to treat all the blocks with the same parent path, exception handling path, as belonging to the same set, and we can flatten each set separately, but not everything as a whole. There is also some problems with the indirect branches because they normally take a block address as a parameter, and everything you do with a block address that it's not jumping, it's undefined behavior. And finally, another obfuscation, it's not rather an obfuscation, it's rather a check, a protection, is to insert some checks in the user's program that will periodically monitor environment to detect if the program is being run, for example, in a jailbroken device, or in an emulator, or if it's being debugged. So for example, in this case, we show a small C source code. This code tries to create a new file in the /private directory. If we are successful, it means that we are running probably on a jailbroken device. So in that case, we will abort execution and try to generate a crash. If not, the execution has to continue normally. The first problem that we encounter when doing this is that the startup checks are not really platform independent. So the LLVM provides a global variable called global constructors. This is a list of function and a function and a priority that will be executed before everything else. However, on Windows, the priorities are broken. They are completely ignored. So we have a patch that fixes this and inserts, according to the priority, the functions on the from the XCA to the XCSIT section of the PE executable. But still there is a small problem. On Windows, you have the TLS constructors that are executed even before all the functions in these sections. So for that, we had to make a horrible hack to be able to execute or start up functions in the TLS constructors. And another problem that we have is that these checks that we perform tend to be really complex. It's not reasonable to implement them directly in the LLVM-IR. So it's typically desirable to implement them in C. But normally in these cases, what you will do is you create a small runtime library to ship with the compiler, or you use compiler RT. However, in our case, a small runtime library will be really easy to identify for a reverser, so it could patch that function and take advantage of that. The solution that we want is to have the IR the IR of the check at the same time as the IR of the user's code, and to obfuscate both of them at the same time as a whole. One solution for this is to pre-generate the IR for these checks in C code for every target, but that's not really practical. So the solution that we found is to do clangception. That means we call clang from within clang. That means we are not going to fork another process. We are not going to perform any system call. We are going to, inside our LLVM path, we're going to create a new compiler instance, forwarding all the target specific options to this new compiler instance. We're going to share the LLVM context with the parent compiler instance, and we're going to compile the check C code, link it with our module, and that. Okay. This has one special advantage, is that we can let the user also write its own checks using the C code, and we compile it and inject them in the user base, in their user code, using our infrastructure. And now I will let Adrien talk.
Thank you, Juan. So I'm going to talk about a small protection that has many issues we encounter with. So if we take the previous function that Juan showed that checks if an iOS device is jailbroken, one property that we would like is to know whether the function has been modified or not. So what we call call introduction is basically some pass, some checks. So we verify that the call hasn't been modified before the binary has been launched. It hasn't been modified at runtime, for instance, by a debugger. So one way to do that is to say, okay, let's take the hash of the whole binary, and let's check at startup if this hash is still the same. The issue is that it's kind of easy to remove. There's only one check to remove, so we can say, okay, let's insert checks at various places. But we can have some potential issues, like if we take a binary like Clang, which is a static build of Clang, something like 60 megabyte binary. It can take something like 20 milliseconds on a modern CPU, which is quite a lot if you insert that, for instance, before every function call. So we kind of also need some better granularity, so we also need maybe function level integrity checks. So the idea is to say, let's compute hashes of functions individually and check this hash at various places like we want. So for instance, we can say at the beginning of every function, we can insert a check. Before each call size, we can verify that the function which is called is actually the good one. We can cross-check function between them, so function foo will check function bar, and vice versa, and so on and so on. So basically how it works, if I take the function foo here, we just say hello world, we insert in this function we insert here these two small lines. We compute the hash of the function and verify it between the static arrays of hashes that we compute. We explain how later. And basically, if the hash is not good, we exit or we crash or we do whatever they want us to do. And we kind of want to do this at IR time. So why? Because it will make this a cross-language, a cross-platform check. We can use what Juan explained to insert the hash function and to obfuscate it like with the user code. And it's kind of hard to do that at backend time because it will become backend dependent, and we don't really like backend dependent stuff. But there are many issues with by doing this at the IR level. We can't actually get in LLVM. First thing, we can get the pointer to the function in the LLVM-IR. So we see how we get around about that. And the second one is that obviously we don't have the hash. We can't compute the hash of the function at IR time because we don't have the final assembly code at this time. So about the end of the function, there's no actual object in the LLVM-IR that allows us to say, okay, I want the pointer to the actual end of the code function. We have a C function pointer. We don't have the end of the function. So one solution is to use derive from LLVM block address. LLVM block address is an LLVM constant object. It lowers to the address of the block function. It has been implemented in LLVM to support undirect gotos. It's an extension from GCC. And so we just have that and say, okay, if I'm asking for the null basic block, just give me the address of the end of the function. And so we had a new object in the LLVM-IR, which we call end-function pointer, which basically does that. There's some issues with that. Is that for the first one is that we introduce an incompatible modification of the LLVM-IR. For instance, for iOS applications, they ship LLVM-IR to the App Store, and so maybe Apple would say, okay, I don't understand this IR, there's something weird in the middle, so I don't accept your application. And it's still kind of a hack. We're not really proud of this one, but it works. About the hashes, also we still got to fix the problem of having the hashes of functions. So the general idea is to put placeholders at the AR time where the hashes will land, and then we use a post-processing tool and the final binary to compute hashes and fix the binary. So by doing that, we need a tool, a cross-platform tool, cross-format, cross-platform tool to do that. So we use a framework developed by Corsa, which is called Leaf, which basically starts from the LLVM ELF PA structures, and which is kind of improved, a lot improved actually. You can do a lot of things with it. It's open source, you can try it if you want. And one issue still with this solution is that it's still hard to obfuscate hash values because we're too late, we can't insert code to generate them. And we also can't obfuscate function pointers for the same reason. And we still have a lot of issues with this solution. So for instance, if we've got dynamic relocation within a function code, the loader will actually patch the functions when loading your binary, so the hash will change. This actually does not happen a lot on x86 at least. It will happen if function is more than 2 GB of code, which is kind of rare, and you have other issues, I think, if you're here. We assume that a function call is contiguous. There's actually nothing in LLVM, as far as we know, that statically say, okay, this will always happen. So it works for now, but may be broken in the future. We also realize an undefined behavior, because in C and in the LLVM-IR also, it's undefined behavior to dereference a function pointer. That's actually what we do. And the last issue we can have is that actually a C function pointer is different in some cases. Is different from the beginning of function code. If we take an exporting function in a DSO, for instance, the C function pointer is just a pointer to the GOT under Linux at least, and the GOT is basically just a jump. So the C function pointer has nothing to do with the beginning of function code. So another way to deal with these code integrity checks is to use another idea. The idea is to use the LLVM JIT to generate the function code at ER time. So basically, if I get my putTest hello world function, at ER time, I will use the JIT and will image assembly, and I will put this assembly in an array in the IR, and then the function will be transformed just to a jump to this array. So the benefits is that we can treat function as a array of bytes, which is kind of interesting. We can do integrity checks on this array, like any other array, and we can make some free on-the-fly decryption, re-encryption of this function. but it's not as easy as it seems. So the first drawback is obvious, kind of obvious. The putTest symbol, if I git it from the Clang process, I will get the address of the putTest function within Clang, which is not the address in my final binary. So I gotta pull all these symbols away in an array and to access disable from this array. The other one is under Linux, for instance. C++ exception frames are registered by the loader. They end up in some kind of section, which is created by the linker. Obviously, it won't exist in this case, so we need to register it by hand. It's kind of hacked. You need to call an internal function of the loader and so on. And obviously, we got the NX issue for encryption and re-encryption, but this one is kind of classical. So it's really hard to make work actually in a cross-platform way. So we have it working on Linux x64, x86, sorry. And we did not try to make it work on Windows because it started really to look like hacks above hacks. So we keep it for historical reasons, but that's it. So now the question is, how do we let the user obfuscate his code with all of this? So obviously we can apply audio obfuscation on all the code. It will make the code really big. It will make the performance really hard, not really good. So we need some kind of locality. And as the user usually knows what he wants to protect and how he wants to protect it, we need to let the user a way to tell us that. So if you look at what exists in LLVM, we have got functional attributes, our metadata, that tells some obfuscation paths some hints. We can activate or deactivate optimizations, sorry. But in the end, the compilation flow is statically written. For instance, it's a path manager builder, and the user has really no way to change that. So what we came up with actually is a set of pragmas. Then we can apply to basic block, to functions, or to a module. And this pragma would say, basically, to the compiler, you need to apply this obfuscation to this function with some potential options. We also can describe that with a YAML file, so it's just for convenience. It's an out-of-tree description. We can say basically the same with the program, but in a separate file. And to make all of this consistent, we describe passes in other YAML files. So we describe the name of the passes, what it do, on which object it works, and the options. And it helps us generate the documentation for the pass, and also the C++ glue that we describe on LLVM pass. So with all of that, we use a factory, a custom pass factory, which will instantiate an LLVM pass object at compiler runtime according to the name of the path and the options and so on. So one thing we still need to figure out is how do we schedule everything. So as Serge had said at the beginning, the first thing we do is that we apply a set of optimization paths. Then we add one LLVM path that we schedule all the obfuscations through, that are declared through the pragma. Whoa. Okay, sorry about that. Yeah, and then we make a final LLVM path that will do the post-optimization stuff. So we kind of need to run Path Manager within an LLVM path to do that. And so it is really a good idea. So if you just create, for instance, in the post-optimizing phase, a Path Manager, use the Path Manager builder to add the passes in it and run it, you have some issues because, for instance, simplify lib codes doesn't have the good information to do the proper work. So we have some target dependency information to add to the path manager, and we need to understand where they come from. So if we look at the Clang code that generates the path manager that Clang will use, we'll see that they are creating by hand the target library of path, for instance. And this one, it depends on the Clang options. And so what we actually need to do in the end is to take these analyses and forward them to our new path managers. And when you do that, you see that the APIs for these analyses are not meant to do that. So we kind of borderline, I think, in what LLVM was designed to do at the beginning. But in the end, if we do that, it works well, and it achieves our goal. So now let's talk about the test and how do we benchmark this.
So now you know how to write an obfuscation or what it is, how a user can use this obfuscation using directives to specify the place where he wants to protect his code. But the most important thing is the obfuscated code correct and efficient? Because when you try to obfuscate code, some things happened. Because you're really not using LLVM for the primary target. So first, you want to do unit tests. But generally, a compiler is predictable and reproducible. But here, randomness is part of the obfuscation scheme. You can't, it's a feature to have random obfuscation so that you don't have all the time exactly the same pattern. And how do you test that? One way would be set the seed, and then it's okay, you're reproducible. But in that case, you only test one code path. So what we did is not fix the seed. So when you run the test suite and then rerun the test suite, you're not running exactly the same tests, but the tests are written so that we check for invariance. So the file check test just looks whether the artifact related to the obfuscation is still there. Does it survive the obfuscation? Does it survive the optimization? Is it generated in some cases? So that's for unit testing. Some obfuscation also are just replacing a simple instruction by a more complex one, but sometimes it's difficult to prove whether it's correct or not. So we use Z-free prover or a homegrown solver called Haribo to prove that these substitutions are always correct. So that's for unit testing. Then we go a step further, Fuzz testing. So we are using Sesmith that already generates some kind of wired code, and then this wired code is obfuscated into some even wilder code, and you generate this kind of stuff that you should not find in regular code base. And sometimes Clang has difficulties with that, but it's okay. We can report the bug and fix it. And generally, we don't have that much problem with that kind of error. And then we realized that obfuscation is a kind of integrated obfuscator, fuzzer, because fuzzing is generating strange input and just observe how it behaves. So what we do is take a regular input, obfuscate it, and then pipe a new obfuscation, and so on. And in the end, you have code that really you would not generate from regular C code, and that tests a lot of boundaries. One step further, we are testing on a large open source project, which attack different kind of patterns. So Lua, CMake, OpenSSL both prove to be very good code base to test our obfuscator. And for each obfuscator, what we do is we pick one obfuscation, we put all the level at the maximum level, and see if we can compile, and if we can compile, whether we can run the tests, and if the tests run, whether we have the correct result. And if that's okay, even if we don't understand anything about what happens, it's just an extra guarantee that the obfuscation is performing as we expect. But sometimes it does not, and especially as we have more than 20 different obfuscations, there are a lot of corner cases that we don't think of to begin with. So we packed all these patterns into a small test suite so that we don't fall in the same pitfalls every time. So for instance, because we support C++ generated code generated from C++, a large object passed by value tends to do not, it translates into a specific attribute in the function arguments. And when you begin to shuffle the function argument or add new ones, you have to take care of that. When a function is declared in weak linkage, if you try to obfuscate it, then it may be replaced by another definition, so the invariant is not always the same, and you have to take care of that too. Basically, anything that deals with exceptions is error-prone when you want to obfuscate it, whether it's in the landing pad or during the unwinding. So you have to take care of that, especially when you clone a function. You have to do some extra bookkeeping. Variadix arguments do not like when you add a new argument on where you shuffle things, so you have also to take care of that. And recursive calls are a recursive source of problems, so we had some issues with that. Anyway, sometimes tests just crash. Like you run the OpenSSL test suite, and you have this test that returns 2 instead of 1. And you don't know anything about OpenSSL, you don't know anything about the tests, but it doesn't work. So how do you debug that kind of thing? Sometimes it's the compilers that crash. And in that case, you have these wonderful tools that have an already obfuscated command line interface, which is called bug point, and you can manage to slim down the bug. But some of the times, the only way to find the origin of the obfuscated problem is go through each file, deactivate the optimization for each file, and then for each function, and then for each basic block until you reach something that you can understand. Because the basic problem is that obfuscation is meant to make things difficult to debug. So when you've got a bug, and it's because of your obfuscation, it's difficult to track things down because if it would be easy, then the obfuscation would be a failure. Some kind of problem we had, set jump. Set jump is used a lot in the Lua interpreter to implement exceptions. And the specificity of set jump is that it returns twice, which is not a problem because there is a special attribute in LLVM to represent that. But this attribute is not set by the GNU libc. This function is not set as return twice by the libc, so we don't have this information. And when you obfuscate some code, you want some invariant, like you obfuscate the code graph, but you want to be sure that each function returns once. And you can't rely on the annotation to put these functions out. Another problem we meet a lot is because we generate very large expression or very large code, sometimes the compiler is not suited for that. For example, during the DAG scheduling, you've got one member that assumes that a short will be enough to store all the information, but it's not in our case. So you meet the assert if you are in debug mode, but if you release like this, sometimes it just hurts. And there is a lot of variance on that topic, like register allocation is not linear in cost. So if you have a very large code, then the compiler does not crash until it memory swaps, and that's not very nice. Or if you're trying to use Valgrind as part of your test suite, and then you realize that Valgrind considers that a function that has more than 1,000 instructions is not a valid function, and it stops. So you meet this kind of problem over and over, but that's the price to pay when you do obfuscation, I guess. But that's only for do we generate codes that has the right behavior. But the goal was to obfuscate code. How do we test or measure that the code is obfuscated? There is in the literature a lot of metrics, like randomness of the output, or you can use engineering metrics like the number of paths in the function. But ultimately what matters is the reversers. But wait, we are in a security firm, so next to my chair, there are some reversers. So what we do, and that's completely not automatic, not reproducible, not scalable approach, but that's the only one that matters for us, is that we do capture the flag challenge. So we prepare a regular code, we obfuscate it automatically, we submit it to our friends that are not going to stay our friends because of what we inflict on them, and we get their report. We watch how they attack the code, because ultimately they achieve their goal in 1 week or 2 weeks, it depends. And then we read their report and try to fix the thing, make their life harder, and then we go over that cycle again. So that's not automatic, but that represents the reality. So that's all for our talk. But before you ask any question, I'd like to thank the LLVM community because I started that 4 years ago, quickly joined by Adrien, and 1 year ago by Juan and Pierrick. So we're not a big staff, but we're being able to ship that 1 year ago, and it's in production. It's used by several companies, and without LLVM, that would be impossible. So thanks for that, and if you have any question, we're open to that.
So we don't have any mics for the audience, but you want to ask a question, stand up and speak loudly, please. As everybody knows, Apple requires shipment of application with bitcode attached. And for example, tvOS has for obfuscation big problem because it's built from bitcode on Apple side before publishing on
the Apple Store. Yeah.
So how you deal with this problem for your integrity check?
For integrity check?
Yeah.
Yeah, that's what I say. Like, as the format of the IR can be different if you use the current integrity. You can have issue with Apple. We didn't had issues for now, so I guess it works. But I think the right way to do it will be to kind of upstream this or find a nice way to do it and have this in the LLVM-IR in the end. We didn't take time to do that now, but I think it's going to be the way we'll do it. I think the proper way to do it, actually.
So the question is, are we running our obfuscator on Clang and then run Clang on the test suite? Is that? So what we did is run our obfuscator on Clang and then run the test suite. It's not part of our regular test suite because that's a very big project, and so our automatic integrated tests already take 2 hours, so we can't pile up too much stuff. So we did that once, and it worked, but it's not. I can't guarantee that it's still okay because that part is manual.
Control flow flattening. If you pass that through the optimization pipeline again, how much of it is left?
So control flattening, it's everything normally is left. But also you have to think that we chain the obfuscation. So maybe you have some obfuscations that you may undo, but if you apply an extra protection, it's protected.
The thing is, as Serge said in the introduction, is that we take really great care to check for each obfuscation if LLVM removes it. So basically, if you just take, even if you just take the control for flattening, it stays in the end. And LLVM actually, the current version can't reverse that.
But sometimes we do have issues because we have our test suite that tests whether LLVM can deobfuscate or not. And we have that obfuscation, which is not homegrown, so I can speak about it, that turns every scalar operation into a vector operation, which is a good protection because some reverse engineer tools don't support vector operations. So if everything is vectorized, you don't lose that much in terms of performance, but you have some kind of protection. And what LLVM does, if you do this in a trivial way, it just say, okay, you're doing the same thing 4 times, so I'm just going back to scalars and removes from them. So we added some extra steps that confused LLVM vector to scalar. But when we switch from to LLVM4, it happens that this optimization improved, and then we had to improve our obfuscation again. And we're going to make the switch to LLVM5, and I expect some extra work on that. But that's part of the cat and mouse game. Yeah.
So kind of as a follow-up to that question, have you checked how well static analysis tools, like outside of the LLVM project, are able to analyze the output of your code versus the unobfuscated code? So
do you think like something like IDA or stuff like that? Yeah. We actually use IDA to check the outputs. IDA is a disassembler, like more than a disassembler. You also have a decompiler. Actually, the static analysis is quite hard because you break a lot of analysis, actually, like people checking data flows and stuff like that. And even if you try to decompile this with the decompiler of IDA, which is X-ray, something like that, it does not give some meaningful information. For some obfuscation, it really breaks things for them. Yeah. So what actually our reversers do is that they use DBIs or things like that to dynamically get traces of what happens, and they kind of follow the data to understand what's going on.
Basically, we are more resilient to static tools than to dynamic tools. Because every obfuscation protects from one kind of attack, and it's more difficult to design an obfuscation that is resilient to dynamic tracing than just static analysis.